All right, so recording has started. So let's start. So this week, what we're gonna do is that the plan is to wrap up Perceptron, and then we are gonna do kind of a crash course on linear algebra because it's the most important type of math that you need for neural networks. So kind of make sure everyone is on the same page. So we'll kind of like run through some basic linear algebra. Not everything, just the things that are crucial for working with neural networks. We'll kind of cover them, and this will also lead to kind of the next topic, which is Hebbian learning. So right now we're covering perceptron, which is a specific learning rule. The Hebbian learning rule is another type of learning rule, and we'll see that with Hebbian learning, we can also do supervised learning, and uh, that can be expressed purely as a linear algebraic operation. So the linear algebra that we do this week, that will help us formulate the Hebbian learning algorithm. So it's gonna be very useful. Uh, Also, I wanted to check, can everyone hear me okay?
Yeah. Also, would you like a note taker or...
Sure. How do you do that? I don't have any experience. Like, is it?
No, would you like a student
Oh,
to
yeah,
take
yeah.
notes?
Thank
Okay.
you. Yeah. Anyone volunteer? Thank you for reminding.
Yeah.
Uh, yeah. Any volunteers for note takers today?
I
If not, I'll just
I
go through the
can
list.
I can take notes for today.
Okay. Thank you, Bobby. All right. All right. So let's get started then. Okay. So uh, let's kind of start with the perceptron, which is what we were talking about last class. Uh, so what was the problem? So we had inputs, right? We had an input which belongs in some space RD, right? And then we had an output label, which can be plus or minus one, right? And then we are trying to learn a, a separator or a hyperplane, right? Which is also in the same dimension as the input, right? Uh, Such that what we want is that basically if you have a bunch of points, right, kind of these circles are one class, and then we might have some crosses as another class, and and you can think of these as images of cats and dogs, and you want a rule that says that if I have a new cat or dog image, I'm going to use this rule to kind of decide whether it's a cat or a dog, right? So when we learn this W, this represents kind of one of a hyperplane, and then this could be the positive side of the hyperplane, and this is the negative side. Okay? And the rule was what we do is that we take a inner product between our vector of weights that we need to learn, right? And if this is greater or equal to zero, we predict that the predicted label is going to be one, and then else, which means if the dot product is less than zero, then you predict it's going to be minus one. right? And then we kind of formulated this as saying that what we want is that for what we have is we are going to have like a a training set of data points where we have these vectors xi, which we can think of images, and you have n examples, right? And our goal is to find a weight vector w such that, like, for all of these, eventually we want that for all of these images in our training data set, we want that the dot product, right? So this is a scalar, and we multiply it by the corresponding uh, label yi. This should always be positive, right? Everyone clear on this rule? Why this is correct? Why does this mean no error? Okay, good. So that means that basically if the dot product is positive and our label is positive, that means we didn't make an error. The other case is the dot product is negative and the label is negative, we also didn't make an error. So our learning rule was such that we ran through the perceptron rule, right? And we discussed this last time. And the perceptron rule was that every time we find a an error where this becomes negative for a particular example, right? So if we find that we have W transpose, all right, if we find an example as we are learning the weight, if we find an example where this becomes negative, had a question? No.
Oh no,
Then
sorry. Didn't realize.
okay. Then we have make an update, and what is the update? We basically we change W to be W plus Y times X, right? So and then we have a iteration count. So if we are currently in the T8th iteration, then for the next iteration, we update the weight like this, right? Okay. And we talked about motivation of why this will make sense. So what I want to do is what we are going to do is I'm going to give you a result that proves that the perceptron algorithm works correctly. Like it converges to a state where there are no misclassified examples. But I also want to kind of give a connection to uh, a general learning algorithm called gradient descent. Okay, gradient. And I think it's important to know the connection here. Uh, Anyone taken a ML course where you've heard about gradient descent? Yeah.
I haven't taken an ML course on it, but
Okay.
the experience that I have working with some
Hmm.
algorithms, I have studied it briefly.
Okay.
But still,
Good.
I don't have a lot.
Okay. That's
Same for
good.
me.
Got it. Thank you. Thanks for sharing that. We are gonna go really deep, spend a lot of time on gradient descent and optimization for neural networks in an upcoming class, but I just wanted to just quickly show you the connection with gradient descent and perceptron. So I'm gonna just briefly explain this, and then later we're gonna go really deep, much more deeper into this, because this is kind of the central learning paradigm for neural networks. So we are gonna cover a lot on this. So the way to think about gradient descent is what you are trying to do is, in general, for any machine learning algorithm, especially supervised learning, you eventually you have some sort of loss function, right? And then the loss function, what you're trying to do is that you want to so the loss function might look like this. So you have your weights, right? The x-axis represents weights, but it can be a high dimensional weight vector. But just for simplicity, I'm just showing one dimension. And this is your loss, right? So for example, if we are talking about linear regression, this was the squared error loss. Uh, and then if it's supervised learning, we've talked about cross entropy loss in the linear classification lecture. So these are all different types of loss examples. Uh, so one type of loss could be like this type of kind of a loss, which is usually a what is known as a kind of a square loss. Usually a square loss looks like this, right? And then the way what we do is that we want to find a value of W which is kind of close to this region, right? So this is the place where the loss is minimum. We'll talk about this later, but this is an example of like a convex function. I mean, my drawing is a bit bad, but this is kind of what is known as a convex function. So what we do is that we might start at some point here, right? And what we do is that at this point we kind of find the gradient, which is kind of we differentiate the loss with respect to our variable W, right? And the loss function is, in this case, it's increasing. The derivative shows that the function is increasing this way. So we take a step in the negative direction of the gradient. So we take a move in this direction, right? Which means that what we're doing is that we are moving W in this direction, right? Or if we had started here, we would kind of move in this direction. And then as we take these steps, we eventually kind of come close to a point where the W is to a point where our loss is very low. And a low loss means that we have a good learning algorithm, right? So basically the general rule is that at any iteration, this vector is going to be WT minus some learning rate, and then the derivative of the loss with respect to the current weight. Okay, so this is the gradient descent rule. So if you don't know it yet, all you can think of is that we kind of update the current weight by moving in the negative direction of the current gradient, right? And this is such an important rule that eventually, if you memorize this rule, that's also fine, because this is basically the learning that is used in a lot of like large scale deep learning models. Uh, so now let's see how this connects to the perceptron. Okay, so in the perceptron, so if you want to frame perceptron in terms of gradient descent, we need a loss function, right? So what is the loss function for perceptron, right? So let's try to define that. I'm going to claim that the loss function for perceptron is something like this. So the loss for perceptron, this is the perceptron loss. Okay. Is going to be maximum of 0 and minus y times W transpose X. Okay. So let's think about this, if this makes sense. So what is our perceptron rule? The perceptron rule is we look at y times W transpose X, right? And if this is greater or equal to 0, that means that we've properly classified this point. So there is no loss, right? And now if you look at this rule, if this is positive, that means this number is negative. So it's less than 0. So the loss is 0. So that means that if we correctly classify a point with the current weight vector, there is no loss and no error. So this makes sense. Otherwise, else, if it's less than 0, right? Then if y times x is less than 0, right? Then if it's less than if it's a negative number, then I'm adding a minus here and making that a positive number, which should be greater than 0. In that case, we have a loss proportional to this number, y w transpose x, right? So that's, and then that is a kind of an intuition of the loss for perceptron. So if I try to kind of plot this, right? So here I would plot y w transpose x on this axis, and the loss is here. So if this is positive, then there is no loss here. So it's like the zero line here. But if the loss is negative, then we do a linear loss here. Okay. So that's the loss function. Okay. So that's our loss function. And now let's compute the gradient of this loss with respect to the weight W. Okay. And now if you look here, this is not a continuous function, but it's kind of a piecewise linear function. So we have this linear part here and this linear part here. So when we take the derivative, we can just take derivative in two cases, right? So what we're going to do is that we're going to compute this in two cases. One is where this is positive, right? If this is positive, then we see that the loss is 0. So the gradient of the loss with respect to del W is also 0. Okay. Else, if it's negative, right? If it's negative, then the loss is y w transpose x. And then if you, so this is this case where this is negative. In that case, we can see here that the loss is the same value, y w transpose x. Now, if I take the gradient of this with respect to w, what do I get? Sorry, what would it be? Was anyone answering?
I just said bless you.
Oh, okay. Sure. Thank you. Okay. So let's go through this. So in this expression y w transpose x, what is the variable and what are the variables and what are the constants?
Is y a constant
Y
here?
is a constant. Yep. So
So
y will come out.
y would
Yeah,
disappear, right?
exactly. Y would kind of come out of the derivative, right? The constant guy would come out. And then we have w transpose x, right? So now let's look at w transpose x, right? And if you take the derivative of this with respect to w, what remains is again x is constant, right? So we'll just have the w vector remaining, right? So this should be uh,
Yx.
yx, exactly. Sorry, this is like a linear function of w. So and x is constant, so we're gonna get yx exactly. Okay, and now uh, if you look at the gradient rule, what we're gonna have is, so we what we have here is this is now going to be y of x, right? And now if we try to say the gradient descent rule, the new weight is going to be basically the weight remains unchanged if there is no error, right? So y, if y x transpose x is greater or equal to 0, and we know that that's the rule where if you don't find any point that is misclassified, then we just don't change anything. But if we find else, what we do is that we're gonna change it by W transpose minus a learning rate times the gradient, which we've computed here to be yx. Okay, all right. So I made a mistake. This is going to be minus, right? Because when it's less than 0, the loss is minus y w transpose x. So is there going to be a minus here and a minus here, right? So then there is a minus here, right? So eventually the learning rule is going to be this minus will go away, and then I'm just going to add a plus here, right? So anytime there is a mistake, the rule is wt plus 1 equal to wt plus eta times yx, which is the same as the perceptron rule that we've known before, right? So it's the same rule uh, as this one, right? The only thing is that I've introduced a kind of a learning rate. You can actually add a learning rate here also. The perceptron typically works without a learning rate. If you set by default, you can set it to 1. But if you want to control your learning, you can also set it to a different number based on your experiments. But we'll talk about learning rate optimization later in this course. But for now, I assume that eta could be 1. Okay. So the point of this is kind of to show that perceptron is not something just accidental, but it's kind of a precursor to almost all like state-of-the-art neural network algorithms. And as we'll see that the perceptron becomes the building block of neural networks. Okay. All right. Any questions so far? Everyone okay with this so far?
Yep, good.
All right. Cool. So now let's so in last class we also kind of gave some intuition as to why the perceptron algorithm might work, right? We kind of looked at uh, when this term y w transpose x is negative, that means that the angle between w and x is wrong, right? We try to fix that by updating w such that the angle is correct for each value, right? So we can make that formal with a theorem, which we're gonna try to prove, which is called the perception convergence theorem. Okay. And what this theorem is going to say is that we're going to we're going to prove this by making some assumptions. Okay. First assumption is what we call linear separability. And what this says is that we can prove convergence only when there is actually at least one line that separates the positive and the negative examples. In other words, the data set is actually separable, right? So we looked at examples of non-linearly separable data sets, right? So if that is the case, then the perceptron is not guaranteed to converge. But if the data is separable, then we can converge, right? So what we're going to say is that to prove this, we're going to say that there exists some W where we're going to assume this is a normal vector, a vector of norm 1 or a unit vector, okay? Such that for all your input data, so you have these data xi and yi, right? For every data point, you would actually eventually correctly classify them, able to correctly classify them. That means that for every such data, if you compute this value, yi times w transpose xi, you're going to find that this will be positive, right? And there is also going to be a separation between 0 and this number, and that separation we're going to call gamma. Okay, so this is an assumption we're going to make. What this means pictorially is, let's say this is your data set, right? This assumption is saying that the positive and the negative classes, there is a it's possible to find a line. There exists at least one hyperplane or line that separates them, like this one. And it also says that kind of there is this kind of separation between any point on one side and the line that we call gamma. Okay, this is the gamma that I'm saying. So they're not only separable, but they're separable by some margin. So gamma is like a margin parameter, which says that there exists this line that can separate the positive and negative classes by some margin gamma. So this is kind of a stronger guarantee, but it helps us make the proof easier. Okay, so that's the first assumption. And then the second assumption is going to be we're going to assume that all the inputs are bounded, right? So we have as input, we have these vectors xi, right? So if this is a vector, we can compute its norm, right? So in usually this might be the Euclidean norm. And if I compute it, I'm going to have an upper bound on this vector. Excuse me. Now, why is this a reasonable assumption? This is reasonable because in general, there is kind of the unwritten rule in machine learning is like anytime you have any input, before you pass the input to a machine learning algorithm, you should always normalize them. And should normalize them by subtracting the mean of your data and then dividing by a standard deviation. Kind of the reason for this is if you do this for all your features, then you get the same scale for all features, and then that makes learning much more efficient. And we'll talk about normalization for neural networks later on, but that's kind of a kind of a well-known technique that we always apply for inputs, right? We always normalize the input before we pass it through any neural network or a learning algorithm. So if we do that, then it's easy to kind of ensure that the norm of these input vectors are always below some threshold. Like in this case, this threshold is R. And here I did not mean to use a kind of a real R. I just wanted to say a constant R. Okay. All right. Okay. So now, was there a question?
Yeah, I was just wondering, is the reason why the data is normalized is it just because of like making the numbers smaller so that they can be stored easier on a computer?
That might be possibly a benefit, but uh, that's so that's an important point, especially for the weight vectors actually. So the weight vectors, if they become really large and you have lots of weights, then you have to think about the storage of the weights. Uh, Typically, you think of the inputs as you might there might be techniques for like streaming the inputs into your learning model. Uh, you read them in batches. So typically, they the storing the inputs is not really considered a kind of a big issue here. The main issue is that you want to normalize them, because if you normalize them, the scale basically. So here is one way of thinking about this, is to give an example. Let's say you are building a model to predict uh, house prices, or right, and then you have two features, like maybe the number of bedrooms, and then the size of the house in square footage, right? Now, if you take just these two examples, you would see that these two integers are, or one is an integer that is like maybe maximum of 5. The other input might be a much larger number. If you don't like normalize them to bring them into the same scale, even before you run the learning algorithm, you are giving maybe higher uh, weight to different. You are kind of treating the variables differently even before you run the algorithm. But if you kind of normalize them, you bring them to the same scale, that means that you can actually now have the learning algorithm figure out like which is the most important factor, or how do you kind of weight the different factors, like number of bedrooms and the square footage of the house, to predict the house price. So it's kind of more about bringing all the inputs to the same scale, which is why you would want to normalize them and bring them below a certain threshold. Okay, good question.
Yeah, that makes sense. Thank you, Professor.
Yep, good question. So now let's kind of go towards the proof. So we can think of initializing the the initial weight vector to 0. Okay. And then we know that the rule is that every time we have a misclassified point, we update it with this rule. So we are gonna ignore the learning rate and just do this to be, let's say it's yt and xt. Okay. And we're gonna say yt is the so if you remember the perceptron algorithm, it said that at every iteration we look for, if we try to find a point that is possibly misclassified. So xt and yt is the point that we found to be misclassified in the tth iteration, and then this is the learning rate. This is the learning rule that we apply, right? So let's kind of try to break this down into steps. So let's see, once we do this update, uh, what happens to the uh, so in our proof we are assuming that there is this separator that is unit norm, and it's a correct classifier. It classifies everything correctly. So our goal, what we want to show is that if we start with an arbitrary weight like 0 vector, we are gonna make only a finite number of mistakes until we actually converge to this weight vector, which correctly classifies the points, right? So the goal is to start from W 0 and reach W, which is the kind of the we assume that this exists, that this linear separator exists, which we are calling W, right? This one. So if we can reach this kind of this optimal weight vector in finite t, in finite number of iterations. Okay. So if you recall the perceptron algorithm, in the perceptron, in every iteration t, we find such a point. And then if we cannot find any such point, that means we converge. So what we need to prove is that for this algorithm to be correct, we need to reach this W, which is the optimal separator, in finite iterations. So after a finite number of iterations, we should be close to this, and then that means that we would not be making any mistakes. So that's the goal. And we want to show that basically we want to show that as we move from W0 to W, we every time we make an iteration like this, we are actually finding a point that is misclassified. So, and we can think of this as a mistake. So we want to show that we only can make a finite number of mistakes until we reach the optimal classifier. Okay, that's the proof plan. Okay, and now we want to basically what we want to do is that we want to compare as we make progress, as we fix the weight vector. Every time we fix it, we want to compare our current weight vector WT and the optimal weight vector which we assume to exist, which is W. Okay, and when they become close by, that means that we're making progress. So we want to kind of see how we are moving towards the optimal W. So one question I have to you is, how can we measure how close WT and W are? Like, is there a way to measure this? These are both vectors, and we want to see how close two vectors are. Is there a way to measure this mathematically?
I might be misremembering, but dot product?
Exactly. That's exactly correct. You look at the dot product, and then uh, with the dot product, you can actually kind of measure, like, are you actually close by, right? So uh, if you are like negative, then you are actually farther away. But as you become more and more positive, you might become close to the optimal. So you can use that to measure. Basically, the dot product measures the angle between these two, right? So when the angle is 0, that means that you are almost same. So very good. That's exactly correct. So what we want to see is that with this learning rule, when we replace WT with WT plus 1, are we getting close to W, right? So that's what we want to see. So let's see what happens. So now let's see WT plus 1. And let's use dot to actually say dot product, right? So now let's substitute this equation. So this represents the dot product between two vectors. So this is WT plus YT XT dot with W. Okay, and the dot product is linear, so we can take these values out. So now here we have the dot product between WT and W plus YT times the dot product with the input XT and W. Okay, and now let's look at this term, right? What is this term? This is YT times XT times W. And now we made an assumption, which is this assumption, that for the optimal classifier W, this value yi W transpose xi must be at least gamma, which is the margin. Okay, and now this term here, this is exactly the same as this term here, right? I'm putting the W later, but the dot product is symmetric, right? It doesn't matter which one is first. So this is actually, now we know that this is actually greater or equal to gamma. Okay. So now you can see here that what we are saying here is that at every iteration, the dot product with the optimal W and our current W t plus 1 is actually increased by at least gamma, because this term is at least gamma. So if this was the how close WT and W is before this iteration, after the iteration it increases by at least gamma. So we are making progress towards getting the W, our algorithm's W closer to the optimal W by at least gamma. Okay. All right, everyone, okay with me on that? So now our initial W0 is 0, right? And now if I apply this rule, what is going to be W1? W1 is W0, and then it's actually going to be at least greater or equal to W0 plus this term is gamma, right? And then if I do W2, this is going to be greater or equal to W1 plus gamma, right? And now if you kind of do this iteratively, uh, and every time you run this is you make one mistake, right? One mistake means that every time you make this rule update, you found one misclassified point, which is a mistake your algorithm made, and you fix that mistake by updating the weight, right? And now if you, let's say you run this, you have to run this m times for m mistakes, then this is going to be actually uh sorry, this is W1, this is actually times W, this is all times W. Okay, I missed the dot product. So the dot product between the mth weight vector after m iterations or m mistakes is greater or equal to it's going to be what? What will be this lower bound here? Anyone? So this is after m mistakes or m iterations. What can we write on the right hand side? Right? If you calculate this, what will happen? This, what is this term? W0 is 0, so this is 0. And if you kind of compute this and add them up, this will cancel, this will cancel, everything will cancel. And then here you're going to just have this gammas, but there are m equations, so there's going to be m gamma, right? So that's going to be on your right hand side. Okay. So what we have in kind of, this is our kind of step one. We have that our, after m iterations, we have this vector Wm, and we have the optimal weight vector, we can lower bound this by m gamma. And that is a good thing because that means that this value is very high, and that means that Wm is getting very close to W, right? So this is our first step that we showed here. Okay. All right. Now let's go to step 2. Okay. So we've kind of got a grip of how this weight, our algorithm's weight vector gets close to the optimal weight vector W. And now let's let's try to see what happens to the norm of the weight vector. Okay. So we have this equation. We are going to look at what happens to the size of the weight vectors as we run these iterations. So we're going to look at the square norm square, and by the perceptron equation, this is Wt plus Yt, again the same equation, times Xt, right? Okay. And now we can expand this, right? What will we get if we expand this? What is going to be the first term? Anyone? You can think of this as like just a squaring a plus b square almost, right? So the first one is going to be the norm of Wt, right? And then we have like twice ab. So what is twice ab? It's going to be 2 times Yt is a constant. And then we just have a dot product between Wt and Xt. So it's going to be Wt times Xt. Okay. And then what is the last term going to be? Anyone?
ytxt the whole squared.
Exactly. And now Yt is what is the value of Yt? It's plus minus 1. So if you take the square of plus minus 1, you get 1. So the Yt is going to vanish, right? So you're going to just have Xt square, norm square, right? And that's because the value of Yt at any iteration is plus or minus 1. So if you square Yt, you get 1. So that's why there is no Yt here when you do the square. Okay, I hope that is clear. Okay, so now what do we know about this term here? Can we say anything about this term here? Is it positive or negative? When do we actually apply this rule?
Is it negative?
Negative, exactly. So we only apply this rule when this term is negative. So that means when we are doing this math, this is going to be a negative number, right? Very good. So that means this term is this term plus a negative number. So that means that we are taking these, this is a square, this is a positive number, a positive number, positive number, and a negative number. So then we can say that this is going to be these two positive numbers minus a negative number. So this is going to be less than these two squares. So from here, because this is a negative number, we can say that Wt plus 1 square is less than or equal to Wt square plus Xt square, norm square. Okay? And now we're going to look back and see that we actually had another assumption, this bounded input norm assumption, which means that we can actually bound this also because this is also an input. So that means we can actually say that this is less than or equal to WT norm square plus the bound R square. Okay? Everyone with me on this? Okay? So now we can actually do the same trick again. All right, good. Is that we start with W1. The first time we make a weight change is going to be W1 square less than or equal to W0 norm square plus R square, right? This is the first mistake, one mistake we made. And then the next time we make a mistake, we're going to make another update to W2. And then this time the norm is going to change by this. Again, W1 square plus R square. This is the second mistake. And just like before, we are going to say that if we make a maximum of m mistakes, that means this goes up to Wm. With the mth mistake, we reach the vector Wm. And this is less than or equal to, again, Wm minus 1 square plus R square. And now if I add up all these equations, we know that this is 0. And then this and this cancel, this and this cancel, this will cancel, and we only left on the left hand side with Wm norm square. And what do we have left on the right hand side? How many R squares will we have here? Same argument as before with the dot product between Wm and W. If we have m iterations here, how many copies of R square do we have on the right hand side? If you add up all these equations, you have m iterations, right? So if I'm adding all these equations, everything is canceling out. We only have R square terms, and there are m equations, so we should have m R square on the right hand side. That's the upper bound. Okay? So that's the second ingredient that we have in the proof. So in this equation, if we take a square root, then what will we get? We can bound the norm of the vector that we get to be square root of m times r. Okay, so this is the second ingredient. And now we are almost done with the proof. Okay, what we want to show is that by the time we make these m mistakes, right, we want to show that we can only make a finite number of mistakes. That's our goal here. Okay, so now in step 3, we're going to combine these two bounds. Okay, so we have this result. This is like equation 2 that we provided. And then we have this one, right? This is equation 1. Okay. So if I write down it again here, we have the dot product between Wm and W is greater or equal to M times gamma. Okay. All right. So if I reverse this, then I can say that M times gamma is less than or equal to Wm times W. And now here we apply something called the Cauchy-Schwarz inequality, which is a very important inequality in mathematics. Which says that the dot product between two vectors is upper bounded by the norm of the vectors. Right, so this is going to be the norm of the Wm vector times the norm of the W vector. Okay. And now what do we know anything about the norm of the optimal vector W? Do we have any information on this? Anyone remember anything about this? This was an assumption, right? We assume that it's a unit norm vector, so we can use that here. Okay. So this is going to be 1, and then we can plug in this into here, right? I made a mistake here, right? So this is there is no square here. Okay. But we can now plug in this upper bound into here. So what we're going to get is that this is going to be less than or equal to square root of M times R. Okay. And now on this term and this term, I can take this, and this is M and this is square root of M. So if I bring it down on this side and divide by it, we're going to get square root of M gamma is less than or equal to R, right? And then from here, we get that M is less than or equal to R divided by gamma square. Okay. And that's actually the end of our proof. Why is that? Because we've shown that what is M here? Can anyone tell me what M signifies here? If you run M iterations, what does that mean in terms of the algorithm? We'll finish this and then we're going to take a short break.
So if you run M iterations, then that means that you were able to find W in
Yeah,
in M.
exactly. And every time you run an iteration, you actually found you made one mistake, because you run an iteration only when you found a misclassified point. So M also signifies the number of mistakes you've made, right? So that means M is the number of iterations or weight updates until you converge towards the correct weight. And what we've shown here is that M is actually bounded by a finite positive number, which is R by gamma square. Now this might be a large number, but it's still a finite number. So this means that the number of mistakes that you can make in the perceptron is finite. That means that you can only run this algorithm a finite number of times, and after the finite number of iterations, you will actually converge to a weight vector that correctly classifies all the points. Okay, so that's the proof that the perceptron makes only finite number of mistakes and it converges on linearly separable data. Okay, so it's 9:04. Let's take a break uh, and come back at 9:10. Okay, sounds good. All right, everyone. Okay, everyone, ready to start? All right, I'll resume. Okay, so before we kind of go to the next section, which is we're gonna start kind of reviewing linear algebra. Uh, I want to make sure that we understand kind of like why this result works. We proved what we've done is that we proved that the number of mistakes that you can make is finite. Okay, that means that this means that the number of iterations for perceptron is finite, which means you cannot just keep running it forever, right? After a finite number of mistakes, you have to converge. Now, why does it converge? Uh, why does convergence mean that we have a correct classifier, right? So we need to understand that, right? So that comes from thinking about these two results here, right? So what does this say? This says that uh, the dot product between our current weight vector by the algorithm and the optimal one W, which we are trying to get close to, increases is at least m times gamma, right? So that means this is large. Now, what we want is that this should be very high. If this is a very high value, that means that uh, that means that Wm can get close to almost get close to W, right? Because if you think about this, like if this is Wm, right? And this is like W, right? As Wm gets closer to this almost becomes the same vector. And that means that this almost becomes equal to W, in which case the dot product is maximum, right? Which is actually the norm of W squared. Now, but this cannot just become infinite. And why it doesn't become infinite? Because of this equation, which says that the norm of Wm is bounded above by square root of m by r, right? So that means that this tries to maximize the dot product, and this is bounding how much large this vector Wm can become. And we know that the W is a unit norm vector. So this means that these two combined make sure that we kind of converge Wm to W, which makes sure that we have a linear classifier that separates the data, but at the same time that can happen in finite number of iterations, which is this bound M, right? This means that the number of iterations is finite. Okay. All right. Okay. Hope that was clear. I will share notes and also some additional notes on this proof after class so that you can read it further and kind of ask me questions next class if you have further questions. Okay, let's move to the second part of today's class, which is kind of we're gonna do kind of a brief review of linear algebra. Okay, and this is to kind of make sure that we are all on the same page as we move towards the core of the course, where kind of matrix computation, linear algebra, multivariable calculus, optimization, these are all based on kind of basic matrix operations. So we need to make sure that we are kind of all on the same page, right? So uh, the first place where kind of matrices and linear algebra comes up is kind of data, right? And kind of model representation, right? Typically, we say that our training data inputs, for example, the image data that we've been talking about, it's kind of a high dimensional vector, right, which is kind of RD, right? And you can, and we've seen that we can also kind of stack kind of maybe our inputs into a matrix like this, right? And this becomes like a n by d matrix, right? Uh, and our models are represented by these weight vectors. A model can be, for example, for perceptron, it's a linear vector, but as we'll see later, this in general can become a, any general kind of m by n matrix, right? And that's what we'll see in neural networks, that at every layer of the neural network, you have a weight vector, which is kind of represented as a matrix, right? So uh, kind of, I'm sure, hopefully this is kind of mostly just a refresher for you, but typically we have matrix operations, right? So if you have a matrix in R n by d, right, and a vector x belonging to d-dimensional space, then you can compute the matrix vector operation, and we know that this would be this would lie in if it's n by d and d times 1, then this belongs to the dimension n by 1, right? Uh, and in general, the matrices themselves form a vector space. We know that, right? So kind of, if I have two matrices of same dimension, right? If they're both in, let's say, R n1 times n2, right? Then I can add up these, I can add these matrices, and that becomes another matrix, right? And this is also in the same matrix space, right? And the way we do this is basically entry-wise addition of the entries. So these two have the same dimension of entries, we just add them up. And the other operation that you can do is you can multiply this by a scalar, right? And then this just multiplies this scalar by all the entries in the matrix, and it's also in this same space, right? So that should be clear. So I want to give an example. Okay. So what I want to do is that kind of show you how the matrix operations come up in a simple neural network, right? So let's say we have a two inputs, uh, a two-dimensional input, which is x1 and x2. Okay. And then we have two nodes here. Okay. So what this represents is I'm gonna add some notation here. This is a kind of a hidden layer unit. So you can think of this like a neuron or a perceptron, and we are stacking these together to form a neural network, right? Uh, and here you have a weight W to 1. Here it's going to be W to 2. And then this is going to be W 1, 2. Okay. And then the output of this is going to be, I'm going to say this is going to be N 1, 1. Okay. So this is going to be my, like, I'm going to call my layer 1, right? And then this is going to, and next I'm going to have a layer 2. Okay. So this output is N 2, 1. And here I'm going to say this value is O 1, 1. And this value is O 2, 1. And then here I'm going to have 3 neurons. Okay. So this output value is going to go into these 3 neurons. And so this is going to go into these 3 neurons. And then similarly, I'm going to have like some weight values here. Okay. And in this case, I'm going to call this N1, 2 because this is a layer 2 neuron. This is the second neuron in layer 2, N2, 2. And this is the third neuron in layer 2. Okay. And this again goes into to compute. This will get computed into output vectors. So let's try to, so this is like a basic simple neural network. You have 2D inputs here, and they get, we multiply them, take weighted combination of them and get an intermediate value. And then the intermediate values, we add a nonlinearity here. Okay. And then once we have the output of the nonlinear unit, we then actually pass it through another layer. And what I want to show is that basically these can be represented as matrices, right? So what do I have here? My first N11 is going to be, actually, if I take these two, I can stack them up as a vector matrix, right? And then if I do this, then hopefully this makes sense. I have X1 and X2. And you see here that N11 is actually W11 times X1 plus W21 times X2, right? So then I can write down the first weight vector. So I'm going to put a 1 here on top of this to show that this is like the layer 1 matrices. So this is 1, 1, 1. And I'm also going to have W 2, 1, 1. And here we'll have W 1, 2, 1, W 2, 2, 1. So we get the output of the first layer by basically multiplying the input with a matrix. And then we get this, basically the O11 becomes a nonlinear unit. So we, for example, we can say we're going to apply a ReLU here, right? If you, we're going to talk about nonlinearities a bit later, but ReLU is the nonlinearity where basically if it's less than zero, then it's zero. And if it's greater than zero, then it's linear. So this is ReLU. Okay. So we just apply this to here, and then O21 is ReLU of n layer 1, the second neuron. Okay. So basically what we are doing, and this is actually the same computation that you would do in any large neural network. You take the input, you multiply it by a matrix, you get the first layer results, then you do a nonlinearity, and then you get the final output after the layer 1, which is like these two values O11 and O21. And then this gets passed through another matrix, right? And this is also going to be a similar matrix multiplication where now you're going to get n1, 2, n2, 2, n2, 3, right? And if you, so in this case, the we have as input. Now in the second layer, this is now the input, right? This is now the input, and this is your output, right? So the output is a three-dimensional vector, and the input is two-dimensional vector. So the input is O11 and O21. And now I need a matrix here, which would be a number of weight values here. So can someone tell me what would be the dimension of this matrix? What would be the dimension of this matrix here in the second layer?
3 by 2.
Sorry?
3 by 2.
3 by 2, that is correct, right? Because this is 2 by 1, and the output is 3 by 1. Exactly. So this would be a 3 by 2 matrix. Exactly. Right? So basically the 3 by 2, because you can see here that you actually have two connections for N1, two for N2, and two for N3, right? And those would be the the different columns that you need for this computation. And once you have this, then these then go through another nonlinearity, and then you get the final. Then these go through another set of ReLUs, and then you kind of keep doing this, and then you keep doing this until you reach your final output, right? So this basically is how the forward pass works in a neural network. And then what I'm trying to say here is that the forward pass computation is all about matrix multiplication. You multiply matrices with vectors, that gives you the forward pass of a neural network. Okay, so kind of getting really familiar with these matrix operations is very important for neural networks. Okay, so we will also look at some additional linear algebra basics next class. I just want to end today by talking about kind of three important spaces, like in machine learning and neural networks in general, that we should all be familiar with. And kind of we've been talking about these spaces without kind of defining them. So just want to make sure that we are on the same page, right? So the three spaces that I want to kind of make sure that we understand are metric spaces, okay, uh, normed space, and then the third one is an inner product space. Okay, and so in in general in machine learning, a lot of times you would be dealing with the very special space, which is RD, which is kind of a Euclidean space, right? And RD is special because it is a metric space, it is a norm space, and it is also an inner product space. So that's when you have RD as your data and also your model space, then usually life is very good. Like you have all the structure that you need. But that may not always be the case, right? So sometimes you have spaces that is just a metric space and not a norm space, or just an inner product space, right? So we want to make sure that we kind of have an understanding of these spaces. Now let's start with kind of the notion of a metric space. So a metric space intuitively is a space where you can measure distances, right? And in general, a metric space may not actually be a vector space. Okay. Uh, so here you would have a set of points. Okay. And you have kind of a distance measure, which is a measure of distance between 2 points. Okay. And this D function has some properties. So if you measure the distance between a point with itself, right, you expect this to be what? What do you expect the distance between the same point be?
0.
0, exactly. And the next property is the distance should be symmetric. So if you swap the parameters y and x, you expect this to be the same. Okay. Uh, Third property is a very important property, which is called the triangle inequality. So if you take the distance between 2 points, x and z, this should be less than or equal to the distance between an intermediate point, xy, plus yz. Okay. So in general, like if you think about RD, then RD is Euclidean space, and you have a distance measure, which is the Euclidean distance, right? So that's an example of a metric space, but there can be other metric spaces, right? So uh, there are spaces that are not Euclidean, but they are still metric spaces. Uh, and we'll see some examples later on. Okay. So next, let's define a normed space. Okay. So a norm space, uh, so we said that a metric space is may not be an actual vector space, right? And we know what is a vector space. A vector space is a space where the vectors, you can add the vectors linearly, and you can multiply vectors with a constants. And if you add two vectors, it's also a vector. And if you multiply a vector with a scalar, that also remains a vector. Those are the properties of vector space. A metric space may not be a vector space, right? Because basically the notion of adding a vector is not really defined in a metric space. There is nothing defined in a metric space that says that you may have addition and whether addition is valid in a metric space. It's just about defining some constraints on how you define a distance between points in a space. And if these satisfy these constraints, then it's a metric space. Okay. What is a norm space? A norm space is actually a vector space where you have a set of points, and every vector in your space has a length or norm defined on it. Okay, so this is a vector space where every vector in your space X has a distance measure. Sorry, has a length measure. So you can measure the length of any vector. Okay, and this function, which is the length function, which is use the double quote, is a function which takes as input any vector in your space, and you output a positive number that represents the length of that vector. And we have some constraints on this uh, length. So if X is any vector, right? If X is any vector in your vector space, then the first constraint is that this always should be a positive number, because negative length does not make sense. Okay. What is the next property? The next property is that if you ever find a vector X such that its length is 0, right? That can only happen if the vector itself is the 0 vector. Okay. So that means that if you have any vector, so in a vector space, there is always a unique 0 vector. And that is the only vector that can have 0 length. Any other vector that is not the 0 vector cannot have a length 0. That's the idea here. Okay. The third property is if you multiply a vector by a scalar, okay. So can anyone tell me why this term is valid? So here alpha is a scalar, which is kind of maybe a real number. Here I'm multiplying the scalar by a vector and taking the norm. Why does this make sense? Can anyone tell me?
Shouldn't the norm be the same? Am I thinking about that correctly or no?
What I'm trying to say, we're going to define what this has to be for it to be a proper norm. But I'm just saying, like, why can I take the norm of this scalar times a vector? What property of a vector space allows this?
Is it because the scalar times a vector is a vector?
Exactly, because a vector space is defined as where you can add two vectors, you get a vector, and then you can also multiply by scalar, and you get back another vector. So this itself is also vector in the same vector space. So that's why, and the norm is defined for all vectors. So this is why it makes sense. Very good. And the constraint is that this should be the norm of the unmultiplied vector x times this scalar with an absolute value, right? So why do we need this absolute value? Because if I don't take this absolute value and this alpha is negative, then that would make this norm negative, and then a norm cannot be negative. So we need an absolute value here to ensure that this also remains positive. Okay. And the fourth property is similar to the triangle inequality, which says that if I take x plus y, and again, this is a valid operation because vectors can be added. So if I add these two vectors, I get another vector, so I can take the norm of that. And this has to be less than or equal to the individual norms of the two vectors x and y. Okay. So now let's say how can we relate a normed space with a metric space, right? So if you have a normed space, from this you can define a metric space. How can you do that? So to get a metric space, you need to define the d function, which is a distance function. So if I have two vectors x and y, right, I can use this norm to define a metric. So I just say that the norm is going to be, I take the difference of these two metrics to these vectors, x minus y, and just take the norm of that. Right? So that means that every norm space can induce a metric space. So a metric space may not always have a vector structure, but if it's a normed space that has a vector structure, and from that norm space you can actually generate a metric space because you can define a distance measure by using the norm. Okay. So the last space is an inner product space. Okay. So an inner product is again a vector space where you can define an inner product, right? So an inner product is like the dot product that we've been looking so far, right? So we can define a dot product as a function that takes two inputs, right? So it's a function on a space X and a dot product which we can denote by this angle brackets. So it's a function from takes two vectors x cross x, and you get a real number. And how do you define it? You have some properties. So the inner product between two vectors with an inner product with a vector with itself has to be positive. That's first property. What is the next property? If you add two vectors and take the inner product with a third vector, then the inner product is linear in the first dimension. So you get the inner product with x with z plus the inner product with y with z. Okay, so it's linear in the first argument, and then you can, for a real inner product space, so we are assuming that we are only have real vector spaces. Here you can swap the first and second argument and get the same inner product, right? So I would want you to kind of think about these properties with some of the operations that we've already done. For example, in Perceptron, we used that inner product has certain properties, which are all the properties of an inner product space. So make sure that you can relate the properties here to the proofs that we've done so far. And the fourth property is that you can take constants out. So if you have a constant x, alpha times x, so it's a scalar multiplication, right? Then you can take the constant out of the inner product. Okay. And it can also be taken out from the second argument. So this can also be equal to x times alpha y. Okay. So these are the requirements of an inner product space. And now, just like before, we showed that if you have a norm space, you can induce a metric space. You can do something similar, is that if you have an inner product space, so I'm going to abbreviate it as IPS, as inner product space. From this, you can get a norm space, NS. How do you do that? Can anyone? So let's say I have an inner product space on X where I have defined, where I have an inner product structure. From this, I want to get a norm space where I have the same base set of vectors, but I want to define a norm or length for each vector, right? So how can we do that? Any thoughts, like how would we define a length function from an inner product function? Let's say you have a space where you can define the dot product between two vectors, and now you want to define a length of a vector. How can you take a, a dot product or an inner product, and from this define a length vector of any vector?
Is it just the dot product with yourself?
Exactly. Very good. So what you do is that you define, basically you define this to be, you take the dot product with itself, and then you would just take a square root, right? And that's how you can define. So if you want, you can always think of, as an example, like RD, right? So in RD, if you have X and Y, it's defined as the summation of I equal to 1 to D X I, comma, Xi times Yi, right? So it's times, right? And then if you do X with itself, what you get is basically I equal to 1 to D. If X and Y are the same, then this becomes Xi squared, right? And then you define the norm as basically the square root of this value, right? So the square root of the summation of Xi, which is exactly in this case, you take the dot product of X with itself, and then you take the square root. Right, very good. So things are always nice for Euclidean space because it's an inner product space, it's a norm space and a metric space, but it's not always the case, as we saw that a metric space may not even be a vector space. And then the most structure you have is with an inner product space, because if you have an inner product space, right, if you have an inner product space, from there you can induce a norm space. And once you have a norm space, you can induce a metric space. Okay. All right. So we've looked at a lot of properties of the spaces. So let's try to kind of uh, just kind of as a brush up of uh, yeah, maybe we'll do that next class, but I want to kind of talk about uh, kind of different types of different types of important norms that you would kind of encounter a lot in machine learning. Right. So right now, let's assume that we are in kind of a Euclidean space. Okay. So we know that Euclidean space is a norm space, but we can define different types of norms. Right. So we can define L2 norm, L1 norm, and L infinity norm. Okay. These are three important norms. In general, we can define on RD, we can define something called LP norm, which is a general type of norm. And the way we define the LP norm for a vector is that, let's say we have a vector X, right? We're going to define this norm to be a P norm. We put a subscript of P here. And what we do is that we take each entry of the vector. So here X is in RD. So that means X is a vector that has X1, X2, up to XD. So it has D real numbers. That's the vector X. So an XP norm means that we take each entry, Xi, okay, and we take this entry and take the pth power of this, and then we sum up from I equal to 1 to D, and then we take this whole thing and square root by 1 by P. Okay, so that's the definition of a LP norm. Let me just fix my summation symbol. Okay, so this is a general LP norm, and so first let's do a sanity check. So if each xi, so we want to make sure that the dimensions match up. So here xi is, we take the pth power and sum it up. So to bring it back into the same dimension, we then take a square root of 1 by p, so that the values are on the same dimension. Okay, now if we take p equal to 2, then we get back our well-known Euclidean norm, which is the norm that we are very familiar with, which is the square norm, right? Because if p equal to 2, then we take the square of every entry, we add them up, and then we do a square root, right? So that should be well-known for us. The other important norm is p equal to 1, right? If I take p equal to 1, what happens? Basically, we are just taking the absolute value of every entry and we're just summing it up. 1 to D. Okay. So just to give an example, let's say I have a vector X equal to, let's say 1 minus 2, 4. Okay. So what is the L2 norm of this vector? Anyone tell me what would be this value? What is the L2 norm of this vector? And what is the L1? Anyone? What do you need to do to compute the L2 norm here, or the Euclidean norm of this vector?
Would the Euclidean norm be 5?
Uh, let's see. So the Euclidean norm would be the square of all these, you sum of the squares. So what do you have? You have sum of squares, sum as num.
I got 21 for the sum of the squares.
Okay, that sounds reasonable because it's 16 plus 4, 20 plus 1, 21, and then you take a
Oh,
square
sorry.
root.
I thought I got 25. My bad.
Okay, yeah. But I think you have the right idea. And then the other new norm is the L1 norm. So in the L1 norm, what you would do, you would take every entry, just take the absolute value and add them up, right? So what would it be? If you take the absolute value of all the entries in X and add them up, what do you get?
7.
7.
7, exactly. So that's your L, L1 norm. And this is a very important norm in machine learning, and we'll encounter this a lot. The other interesting norm is the P infinity norm. This is a very interesting norm. So how do you define it? So let's see. So if you look at the P norm, right? Basically, what we're trying to do, we are trying to take the limit of P goes to infinity of the summation I equal to 1 to P of xi to the power P, and then you have a 1 by P here. Okay. And now let's think about what is happening here. So you have a summation of these xi's to the power P, and you have the absolute value. Now, as P goes to infinity, what happens here? So let's say you have a vector like 1, minus 2, and then 11, right? And each of these like gets powered. You have 1 to the power P, and then this becomes 2 to the power P in the sum, right? And then this becomes 11 to the power P, right? And then what you're doing is that you're making this P very large. P goes to infinity. Now, when P goes to infinity, what happens to the relative values of these three terms? Which one will dominate the sum?
Would it be 11 to the
It would be 11, right? Because as P goes to infinity, these are positive numbers. At one point, as P is really large, then compared to this one, these two are like negligible. So in the limit, you might as well ignore these and only consider this to be equal to the max of xi to the power P. So in the limit, this becomes what? This becomes the, basically you just take the max of all these i's, right? And you just consider that this is like equivalent to this to the power P. And then you have a 1 by P over here. And then this becomes, now there is just one term, so that max term, and then this 1 by P. So basically this becomes max of I x I term. Okay. So this is called the infinity norm of a vector. Another important norm. So if you go back to our example here, what would be the infinity norm of this vector? it's much easier to compute compared to the others, right? What would be the infinity norm for this vector? Anyone want to try?
It would be the whatever value has the largest.
Magnitude.
So 4.
4, exactly, because you take every value, you take the absolute value, so it's going to be 1, 2, and 4, and 4 is the maximum. So in this case, it's going to be 4.
Okay.
Yeah. So these are very important metrics. These are very important norms in machine learning. What I want to do is kind of draw some pictures related to these norms, and we'll end there. So uh, what we usually kind of, just to kind of understand these norms, we draw the unit norm balls. And because of we're out of time, I'll just gonna draw these and then we'll start from here next class. So the norm ball is kind of defined as kind of me1 is kind of all vectors in your space such that the particular norm is less than or equal to 1, right? So now if we do this for, let's say, let's call this the B2 is the usual Euclidean norm ball. So let's say I'm in two-dimensional space, x1 and x2. If I try to draw the vectors that have Euclidean norm less than 1, it will turn out to be this circle, right? Because in this case, what does this represent? This represents, when I say unit norm is less than 1, then that means that x1's, the norm of this vector in 2D is x1 square plus x2 square, and that has to be less than or equal to 1. Okay? And now, if I think of the 1 norm, then this is defined for a two-dimensional vector to be x1 absolute value plus x2 absolute value. And if I want this to be less than or equal to 1, what type of shape would I get? Any guesses? What would it look like? So if you look here, let's say x1 and x2 are both positive, right? Then this becomes x1 plus x2 less than or equal to 1. So that's like a line like this, right? So everything from here to here, this region is a vector that has L1 norm less than or equal to 1. And if you kind of change the signs around, you're going to get something like this. Okay, so this is the L2 norm ball. And these pictures you would see a lot. That's why I'm kind of trying to cover this. And I'll also kind of I'll talk about this later in next class. But the L infinity picture would actually look like this. And I don't have time today because we're out of time. But I'm just going to draw this and then I'll let you go. But this looks like a square. That's what this looks like. So this is x1 and x2, right? Where this infinity is defined as basically the max of x1 and x2. So if you kind of trace out this, you would see that all the points, all the vectors that lie within this square would have norm less than or equal to 1. And that's why this looks like a square. All right, so I think we are out of time, so let's end here today. And uh, next class we'll continue with linear algebra review, kind of covering some more important concepts that we would need in the course. And then after that, we'll continue. So that's the end of the class. All right. Uh, any any questions so far, or?
Do you just want me to email you the notes tomorrow
Oh
morning?
yeah, that sounds great.
Okay.
Yeah. So hopefully, I think I'll be able to be back in class on Wednesday. One thing I never mentioned is about office hours. So I don't have like a physical office space, which is why I don't have explicit office hours. But uh, every class I would hang out after the class for like 20 minutes, 20 to 30 minutes, so that that would be the unofficial office hours. But if anyone needs more time, like I'm open to doing Zoom calls if you need to kind of meet with me for any to discuss anything. I'm also open to kind of doing one-on-one Zoom calls for to answer any questions. And also the Discord channel is a quick way to kind of get answers from me. But in general, for office hours would be like after class, I would hang out, and if anyone has any questions, I would try to answer them. That's kind of the plan. Except for today, kind of it's a online class. So I'm not sure. Like, I'll be here if anyone has any questions, or you can also ask me next class when I'm hoping to be back in the university. Yep. All right. If no other questions, let's end the call today, and I hope to see you all Wednesday in person.
Thank you, Professor.
Yep.
Thank you.
All right. Take
Thank
care,
you.
everyone. Good night.
Thank you.
Good night.